Hello everyone, thanks for tuning into this video. Today let us see equivalent circuit of a solar cell. Before going into the lecture, I would like to request you to subscribe my channel. So here equivalent circuit for a solar cell is important for analyzing a performance and also determining its efficiency. So in the equivalent circuit we can see a current source, a diode and two resistors RS and RSH. So here we represent the IL, that is photo generated current. So whenever we incident solar radiation on the solar cell, the current is generated. That is, as it is generated due to photons, we call it as photo current, and so that we represent with IL, that is current source. And next we have a diode. This diode actually it represents the current in the dark condition. So here this diode is acts as a sink for the current, and some of the current that is passes through this diode and it doesn't reach the load. So here this diode current actually represents the leakage. It represents the recombination which occurs in the solar cell. So more the recombination, more will be the diode current, and it cannot reach the load here. So diode should be good quality to reduce this leakage current, and hence next we have two resistances RSH and RS. These are there because the solar cell is not an ideal diode. So we have this RSH and RS which represent the corresponding resistances. So we have RS which is due to the bulk resistance of semiconductor. So the semiconductor material which we use for PN junction, so that semiconductor material has a resistance, and next we have bulk resistance of metal electrodes. So to take current and power from the solar cell, we connect metal electrodes to the P and N type materials. So these metal electrodes have also resistance which aid to the series resistance, and also there is a contact resistance between semiconductor material and metal electrode. So all these resistances we combinedly represent uh, so we combinedly represent with as RS. And next we have shunt resistance RSH. So here series resistance will drop the output voltage, that is, so here the drop across this resistor is I times RS. So the voltage that we get at the load will reduce if RS is more. So it is desirable to have a low value of series resistance RS. And next we have this, and this increase in series resistance causes decrease in the maximum output power. And next we have shunt resistance which is represented by RSH. It is the result of leakage across the PN junction around the edge. So it is about leakage and also crystal defects. So every crystal has a defect. Monocrystalline has very low defects, whereas a polycrystalline um, has more defects. So monocrystalline silicon will give more efficiency because of this. Hence, crystal defects would lead to RSH and also pinholes. These pinholes arises due to lattice mismatch between different layers of the solar cell. And also there might be some impurity precipitates like organic compounds or inorganic impurities that are present in the semiconductor material, and this also causes RSH. So here it is desirable to have a large value of RSH. So if the RSH is more, then the solar cell is good. So when RSH is more, it takes less amount of current. So most of the current will reach the solar cell. And so otherwise, if the RSH is low, then it acts as a sink for the current, and that will reduce the power to the load. Hence, these the value of IL, I naught, RS and RSH. These are dependent upon the physical size of the solar cell. And from the equivalent circuit, we have seen IL, RS, and RSH, and we will see IO further in this lecture. And the amount of photo generated current IL will increase slightly with increasing temperature, because when temperature increases, band gap of the semiconductor material decreases, so it can absorb more amount of solar spectrum. That is, as band gap decreased, most of the solar spectrum can be so it will result in slight increase in uh, that is a photo generated current. And next we have the diode current. So here in this we have represented this diode current ID. Now this ID is equal to IO into e power Vd by neta Vt minus 1, where Vd is the voltage across the diode and neta is diode ideality factor. This depends on the material, that is varies from semiconductor to semiconductor. For silicon it is like 2, and for germanium neta value is 1. So it basically depends on the semiconductor material which we are using here. And Vt is the thermal voltage and IO is the reverse saturation current. Now here Vt is thermal voltage, which is equal to Kb uh, T by Q. So here Kb is Boltzmann constant, T is temperature in Kelvin, and Q is charge of electron. And Kb is 1.38 into 10 power minus 23 joules per Kelvin. So this gives us the diode current. So here it is desirable to have a low value of diode current. And next we have reverse saturation current IO. This reverse saturation current IO depends on the material and doping of PN junction as well as temperature. So we have IO. This, when we derive this formula, we get K T power M e power minus Vg naught by neta Vt. So here K is not Boltzmann constant, it is another constant which depends on the dimensions and metal properties. Now here Vg naught, so here Q times Vg naught is nothing but band gap of material in electron volt. So band gap is related to uh, the, the reverse saturation current. So what happens as the band gap increases, the reverse saturation current will reduce. So reverse saturation current for germanium, so germanium band gap is low. So reverse saturation current for germanium will be more. Hence leakage current for germanium will be more, as this is as it is related with this e power minus Vg naught. So as Vg naught increases, I naught decreases. So silicon has low leakage current compared to germanium. And now here K is a constant, so that we have seen. And next T is temperature in Kelvin. So I naught is also depending on temperature, and then M is the factor which depends on the material. So for silicon, M is 1.5, and neta is diode ideality factor, which we have seen in the previous equation, as well as we have seen Vd is thermal voltage. So this is the end of this lecture. Thanks for watching, and please subscribe. And in the next video, let us see solar cell parameters. So please check that out to get a complete understanding about the solar cell parameters. Thank you so much.